Hey biologist, Mr. Fott here. Today we're going to be talking about energy molecules. First up are the need to knows. So we're going to be talking about how electrons from this energy molecule called NADH and an additional one called FADH2 are passed to a series of electron acceptors in the production of ATP by this process referred to as chemiosmosis that we're going to be talking about. Additionally, we'll be discussing the roles of mitochondrial membrane, the proton, which is the H plus gradient, and ATP synthase, another one of our enzymes, and generating ATP. Before we get into anything, I want to talk about this for just a second in case anybody didn't happen to have a chance to learn this in chemistry class. There's an additional type of chemical reaction referred to as a redox reaction, which is actually an abbreviation of the two different halves of the chemical reaction that are taking place. Sometimes referred to as reduction oxidation, thus put the two words together, the beginnings, you get redox. Where there's a reduction, there's always an oxidation, and vice versa. So basically what's going on in this reduction and oxidation, these two halves, is that when something is being oxidized, it's actually losing electrons, and when something is being reduced, it's gaining electrons. Now, if you think of it like at its face value here, reduction typically means a subtraction in something, but we're gaining electrons. But think about what we're gaining here. We're gaining negatively charged particles is what we're gaining here. And so the reduction is more so referring to the charge. It's a reduction in charge. So there is the top, which is like the generic equation. So you have your X's and Y's. Those are just generic chemicals, whatever they happen to be. But notice how there is an exchange of the electrons. One of them is going to lose or donate the electron, whereas the other one is going to accept or gain the electron is what's going to be happening. Now, in our chemical reaction, we're going to be talking about this time around cellular respiration. So here is our chemical reaction down below for cell respiration. So we're starting off with our glucose plus 6 molecules of oxygen producing our 6 waters and 6 carbon dioxide. In this case, we can see that the oxidation portion, the loss of electrons, it starts with glucose is losing the electrons and becomes carbon dioxide, whereas the oxygen is going to be gaining those electrons ultimately to produce the water molecules. And in the end, what we end up with, of course, is the whole purpose of the cell respiration is this ATP production. Okay, so again, I just wanted to recap very briefly. I will not be evaluating you and assessing you specifically on redox reactions. We're only going to talk about it in the sense of gaining electrons and losing electrons, and that's about it. Here it is in another type of chemical reaction, the combustion of methane gas. So basically, this would be like if you happen to have a gas stove at home, this is this chemical reaction going on. So you have your CH4, that's your methane gas, combusting with oxygen gas, then producing carbon dioxide and water. Very similar, actually, to our glucose chemical reaction. The only thing that we're swapping out is the methane. So the methane is getting oxidized, losing those electrons, whereas the oxygen is being reduced and gaining those electrons. Okay, so why we're talking about this whole electron business does have to do with how the ATP is going to be produced ultimately here. So energy, where we actually get this from, starting from our food, our glucose, if you will, broken down, is going to fall, quote unquote, go through a series of chemical reactions, thus the reaction arrows here in between, ultimately ending up at what we refer to as the final electron acceptor, which is our oxygen molecule here. So we have this kind of intermediate, this NADH, and then coincidentally our FADH2 will also fall into this very similar category here. Basically what's going to happen is that we have two different versions. We have the unenergized, which is our NAD+. So this is without the energy here because, again, it's missing that electron and it's missing the hydrogen to help form the bond to hold the electron here, and referred to as an electron acceptor. Once it picks up some of those electrons, as well as some hydrogen here, it becomes NADH. Now it is storing the energy. So this is similar to our ATP molecule in that it's a storage of energy, and once this becomes used, then it's going to go back and revert to its unenergized form, the NADH, in a cyclic fashion, much like ADP and ATP will then do. Once we get to the electron transport chain in this whole process here, ultimately those electrons are going to fall, quote unquote, as we'll demonstrate in a moment here, down to our oxygen molecule to make our water, thus releasing some energy. So this NADH, we're not going to get into its specific chemical structure or anything, so you don't need to memorize any of this. But this is basically just kind of summarizing what's going on here. So our NADH, the unenergized, no energy form, is going to pick up some hydrogens as well as those electrons here to become NADH. So we're going from NAD plus, the unenergized, to NADH. It is now the energized and has then been reduced. It's gained those electrons and is ready to dump off those electrons to move forward to produce the energy. Ultimately here, this is what's going on is we're kind of doing an internal combustion chemical reaction, which is kind of strange to think about, but very true. As one of the first examples I gave us was the combustion of methane gas is very similar to the breakdown of our glucose molecule. The main difference, though, is that when we do so in, let's say, a stove, for instance, that it is an uncontrolled chemical reaction, and we get this massive release of energy all at once. And so it's very like spontaneous kind of thing, right? Whereas in cell respiration, we're doing a similar process. Not that we have these mini explosions going on internally, but we are then losing that energy, or releasing that energy, I should say, to those ATP molecules. But we're doing it in a much more controlled manner. And so it's not just released all at once. It's actually going to be in a series of steps or series of reactions here that the energy will slowly be released and then absorbed into our ATP molecules, ultimately here producing our same product of water. So we have a few different ways that we can then get our energy molecules out of this. One way that we can get the ATP molecule, and we'll come back to our NADH and FADH2s in a moment. The first way for our ATP to be produced is referred to as substrate level phosphorylation. So I think I mentioned last notes that the word phosphorylation just means attaching a phosphate, attaching that P with a circle around it. That's all that means. So our ATP can come in, drop off that phosphate here, and then it can then activate something or deactivate something in a similar fashion. An enzyme can reattach that phosphate is what it can do. So we go from our unenergized form, ADP, adding that inorganic phosphate to produce ATP molecule. And again, here's our enzyme with the substrate. Is then going to be transferring. So the enzyme is helping with the transfer of this phosphate from the substrate is what ultimately is going to go on. And this is one way that our body can then generate ATP molecules. Now, the two other ways that we're going to talk about here is going to be the process of the electron transport chain. Mostly, this is our third phase in cell respiration, which will break down in the next phase. This phase, we're just going to talk about how our energy molecules, what they are, and how they're produced. But this is going to take place in our mitochondria, specifically on the membrane here. It's going to yield a huge amount of ATP, anywhere from 26 to 28 ATP molecules, which is massive. So this whole process here, both of the electron transport and chemiosmosis is how you pronounce this, are referred to as oxidative phosphorylation. And in the title, and as it kind of suggests, you can imagine that oxygen is going to be a part, and phosphorylation, attaching of phosphates, thus the production of ATP molecules. Now, in this chemiosmosis process here, we're going to look at how hydrogen ions are going to be pumped, quote unquote, pumped across our membrane. So we've seen this before, where molecules can then pass through a membrane using one of our proteins here, and then allows it to then attach or phosphorylate that phosphate to our ADP, thus resulting in an ATP molecule. So first up is the electron transport chain. What is ultimately going on here is there's a lot going on, to be quite honest. So you notice a lot of giant purple blobs, a lot of like little acronyms here. Do not memorize any of this. They all do have names. It is like a senior level college level class that you'll talk about all these different things, biochemistry specifically. Don't worry about any of that. Basically, to summarize what's going on here is that there's a series of steps, quote unquote steps, if you will. And again, this is the controlled release of that energy. So we're going to transfer those electrons. Notice how there's two energy molecules here. So here's our NADH, and then we have our FADH2. Both of these are now going to lose their electrons. They're going to become oxidized, and then they're going to give up their electrons. So if you follow the arrows, it's losing those two electrons to become unenergized, NADH. FADH2 is going to lose those two electrons to become FAD. And additionally, we'll see in just a moment, they're going to lose those hydrogens and dump them off into the next phase, our chemiosmosis. But basically, we're going to slowly lose this energy, going from a higher energy state all the way up from 50 to a much lower energy state. We're dropping downwards. So again, the final electron acceptor is going to be our oxygen molecule producing our water ultimately here. This does not directly make ATP. So if you notice, ATP is not directly involved in this electron transport chain. And actually, the ATP is going to come into the next step. So why this is even going on is more so for the next phase, our chemiosmosis. But when we release those electrons, they do have to go somewhere. Because again, we can't create or destroy things. Things have to be transferred is what they have to do. And that's why I refer to this first before getting to our second phase. So now ultimately, here's a little bit better of a diagram. This is a good one to be able to read and interpret, a little more manageable. So we have our energy molecules, NADH and FADH2. And as we mentioned, they're losing those electrons, but additionally, what they're also doing is losing the hydrogens. Now notice we have two different sides. Here's our membrane, the heads with the squiggly tails. We have the inside, here's our inner membrane space, and here's the outside of the membrane, the mitochondrial matrix that we have going on. So we're dumping all of our hydrogens into the inside space is what we're doing. We're driving that concentration to rise dramatically is what we're doing. Additionally, something else to keep in the back of your mind, if we have lots of hydrogens, what's happening to the pH? The higher the concentration of your hydrogens, the lower the pH, the more acidic it is. AP would definitely ask you a question along those lines as to why specific regions of the mitochondria might have different pH levels. Just an extra thought there. But again, this is the point of this whole process, is not, for right now anyway, to produce ATP, but to lose those electrons, ultimately going into oxygen to produce some water, but more importantly, to drop off the hydrogens. And those hydrogens are needed for the actual ATP production. And here's the real moneymaker here. This is this chemiosmosis. So this we call energy coupling is what's going on here. So it needs a little bit of a kickstart. So it's going to take a little bit of energy to get this whole thing going. But what this is doing is, this is kind of like, imagine a windmill or like a wind turbine, or even like a water generator, like the Hoover Dam kind of thing. So how those generally work is that they will turn a turbine to physically cause mechanical motion, and then it will allow something to happen. So in this case, what we're doing here is we're allowing the phosphorylation, the attaching of that phosphate. It's going to mechanically drive them together for the bond to be formed between ADP and our phosphate, thus the phosphorylation. And so what we see here is that the hydrogen must be filed through, and it wants to move in a fashion to go from a high concentration to low concentration. Notice where this is again, inner membrane space. We just dropped off our hydrogens from NADH and FADH2. We dropped them all off. So this is a high concentration of hydrogens to a lower concentration of hydrogens. So they want to naturally flow in this direction. When we have this flow, this enzyme, ATP synthase, this is the one that's going to turn the turbine to phosphorylate or attach that phosphate to our ADP molecule to make our ATP. This is actually where we get our energy from, is by using this proton or the H plus gradient is actually the one that's doing this work. This diagram here does a pretty good job kind of summarizing this whole thing. Again, the whole point of this series of notes is just to talk about our energy molecules. What are they? What do they do? And how are they going to be produced? So again, we have our NADH, FADH2. These are just going to be energy or electron carriers here that we're then producing through our series of steps. They're going to drop off their electrons, ultimately going to oxygen to produce our water over here. And then additionally, they're dropping off the hydrogens. That's the moneymaker again, is that we want to drop off all those hydrogens. Now we have a high concentration of hydrogens inside on the inner space, and it's going to want to move to a lower concentration on the outside. This is the process of chemiosmosis. This is where we're actually producing the bulk of our ATP in this sense. If If you have any additional questions, please let me know. I'm sorry if this is a little bit confusing. We will, of course, be talking about this in much greater depth as we go along. Thank you very much.